Hi everyone, in this video I'm going to be running my K-means machine learning PySpark program from my single node big data virtual machine. The dataset that I will be manipulating is the DNA short reads Treemap frequency matrix that I generated in challenge 3. So I do recommend you check out my previous video before continuing with this one. Each entry in the dataset contains a 64 length list or vector which represents the frequency occurrence of each of the 64 Treemap possibilities that could be present within a short read. Based on this dataset, the aim of the program is to cluster DNA short reads which have similar compositions based on their Treemap frequency vectors using K-means clustering. The structure of this PySpark program follows a machine learning workflow which consists of data loading, data transformation, the creation of sub-datasets, parameter tuning, optimal model training, cluster predictions, and then we'll review the outputs. I developed this PySpark program using a Jupyter notebook where the data was stored in a Hadoop distributed file system. I will be accessing the data via Hive and using Spark as my processing engine, with Python as the programming interface. I'm now going to take you through my code at a very high level and walk you through my machine learning workflow of this program. So the first thing I'm going to do is set both the Spark and Hive context, as this will allow me to interact with both these technologies from my Jupyter notebook. I'm then going to load in the Treemap frequency matrix, which is stored in HDFS via Hive into Spark. Once that's done, we can then do some data transformation in order to get our RDD into the correct format to input into our K-means machine learning model. So what I did was take each entry in my current RDD and converted it to a NumPy array of type float. And the K-means model can take this in as it is now the correct format. Moving on to the next stage, I created 4 sub-datasets from my original dataset that I loaded in, and this was to eliminate a concept called data snooping, which at a very high level means that you must use a different or fresh dataset in tuning, evaluating, training, and predicting your model to eliminate any biases that you could get when working out the accuracy of your model. I created 4 datasets, which are the training set proper, validation set, and test set. And I'm going to be using these different datasets in different stages within my machine learning workflow throughout this program. I then have a function that calculates the Euclidean distance between 2 vectors. And the 2 vectors that I'm going to be calculating the distance between is a data point and the center of the cluster that it's assigned to. And the reason to do that will be explained below, because we want to then calculate the within cluster set sum of squared errors. So at a high level, what this calculation is, it works out the total sum for the distances or Euclidean distances between each data and the center of the cluster it's assigned to. So for each entry in our data set, we take the Euclidean distance between that, this center of the cluster it's assigned to, and sum that up for all entries within our data set. And the value that we get out of it is called the WSSSE score, which is essentially a measure to calculate the variance between the data points assigned to a cluster and its centroid, or essentially how compact the cluster is. And when choosing a K-means model, we want this number to be relatively low. We can then use the WSSSE score in our parameter tuning stage. So the main parameter in the K-means model is K, which is the value of the number of clusters we want to cluster our data into. However, we may not know this value off the top of our heads. Therefore, we need to perform some parameter tuning in order to determine this most optimal value. So using the training set proper and the validation set, what I did was train multiple K-means models using different values of K, which range between 22 and 40. Trained this model on the training set proper and evaluated it on the validation set, and then generated the WSSSE score for each of these 38 different models with varying values of K. Once I then have these 38 WSSSE scores, for different values of k, what I then can do is plot an elbow diagram. So the elbow diagram plots your value of k, in my case between 2 and 40 along the x-axis, and on the y-axis it plots the corresponding WSSSE score that was generated through the parameter tuning, which remember is a variation, the variance between a cluster and the points around it. So once we've visualized this, and this will make a lot more sense in the outputs when I show you, but we can then determine the optimal value of k by identifying the elbow in the graph. Moving on, now that we know our optimal value of k, what I'm going to do is train a completely brand new k-means model on our fresh dataset. So we use the training set proper and validation set during our parameter tuning phase. However, we don't need this anymore as it will introduce biases. So now we can create a new k-means model, training it on our training set, putting in our optimal value of k that we've determined. Once the model is trained, we can then pass it our test set, where we're going to cluster all the Treemap frequency vectors in that test set into our k clusters, and that outputs a new RDD which contains the cluster each short read has been assigned to. Taking this prediction output, what we can then do is create a new dataset which consists of the ID of the Treemap frequency vector, another column for the Treemap frequency vector itself, and the final column is the cluster that it has been assigned to. Finally, what I then did was visualize the amount of short reads that have been assigned to each cluster using Python's matplotlib and a library called Squarify, where I was able to visualize the tree map. Then we have our main method where we start calling each of the functions mentioned above in our machine learning workflow. So we load in our data, convert it to an RDD. We then do our data transformation to convert everything to a NumPy array or vector of type float. We can then split our dataset into the 4 datasets that we mentioned. We can then take part in our parameter tuning, take the WSSSE scores from the parameter tuning of all 38 models, pass it in to visualize elbow diagram. From the elbow diagram, we can determine the optimal value of k. Based on this optimal value of k, we can then train our new model and apply it to our test set to be able to cluster all the Treemap frequency vectors in the test set into the k clusters. Finally, we can show our output dataset and then visualize our results. So I'm now going to run this program and we can see the outputs it produces, and hopefully everything will make a lot more sense. So I'm first going to be asked for some user inputted value. So would I like to enter debug mode? Let's set that to no. It then sets the Spark and Hive context to allow us to interact with both technologies. And then we're asked how many Treemap frequency vectors would we like in the initial dataset to train and build the k-means model. Let's read in 1000 short reads. Now this program is going to take about 2 minutes to run, and as it must go through all the parameter tuning, generate those 38 k-means models to identify the optimal value of k, and then train a new model and output all the visuals. So I'm going to come back in a second and show you guys the output of the program. So midway through execution, what we're outputted with after the parameter tuning phase is the elbow diagram, which, as I mentioned, plots the WSSSE scores for the different k-means models trained on different values of k between 2 and 40. And here we want to identify the optimal value of k by picking out the elbow in the diagram. So as you can see, it kind of looks like an arm, and we want to pick the value of k as low as possible, such that the WSSSE score just stops fluctuating as much and kind of plateaus a bit. Because if we were to increase the value of k even more, you can see that the WSSSE score doesn't really change much. However, if we move back up the graph, it starts increasing quite a bit. So to me, an optimal value of k looks like 18, because this is where the WSSSE score starts to flatten out and there's not much variation by increasing k. So I'm going to input the optimal value of k as 18. The program will then train the new k-means model and output the results. So here we can see our output dataset. So I'm just looking at the first 10 Treemap frequency vectors in the test set, and we can see the ID, the short read Treemap frequency vector, and the cluster it's been assigned to. Scrolling down, what we then get is a Treemap visual, which shows the number of short read Treemap frequency vectors that have been assigned to each cluster. So for example, we can see cluster 2 has a count of 18, cluster 1 has a count of 38, and cluster 0 has a count of 29. And finally, at the bottom, what we're given is some performance statistic. So data loading took 29 seconds, data processing took 194 seconds. Therefore, in total, this program executed in 220 seconds.